One of the most useful things for chemists to understand about reactions is how fast they occur. The rate of reaction is defined as the change in concentration of the reactants or products per unit time. Controlling the rate of reaction and understanding the processes by which reactants change into products are essential skills for production chemists. They need to be confident that when production is scaled up, the rate of reaction remains the same, otherwise there could be cost or health and safety implications. There are two main practical approaches to measuring the rate of reaction: the initial rate method and the continuous monitoring method. The simplest initial rate experiments involve measuring the time taken for some easily recognizable event in the reaction to occur. An advantage of this method is that the concentration remains close to that of the initial mixture and can be easily calculated. In this video, I'm going to demonstrate a clock reaction. We will then carry out a second experiment using the continuous monitoring method, by measuring the volume of gas produced by a reaction every 10 seconds. The continuous monitoring method provides us with plenty of data, however further calculations are required to determine the exact concentration at different points during the reaction. There are many other examples of using continuous monitoring to measure different properties, like colour change by colorimetry, pH by a pH sensor or meter, and temperature by a temperature sensor or probe. Another approach is to monitor the change in concentration by periodically taking a sample and determining the concentration, for example by titration. To explore the initial rate method, we are going to look at the iodine clock reaction, where acidified hydrogen peroxide reacts to a solution containing potassium iodide, sodium thiosulfate, and starch. When carrying out initial rate experiments, it's always good to know what change you're expecting. Here, we're expecting a change from a colourless solution to one that is blue/black. I'm just going to pop my goggles on before I start the experiment. Wait for it. As you can see, our solution has changed from colourless to a blue-black colour. I am now going to perform an experiment where I change the concentration of hydrogen peroxide and measure how long it takes for the reaction to occur at each concentration. We are going to use 5 different concentrations of hydrogen peroxide. As such, I will need 5 conical flasks, which I will label A, B, C, D and E. I'm now going to prepare our reaction. To start with, I will add a solution containing potassium iodide and sodium thiosulfate to each conical flask. We are now ready to start our reactions. However, before we begin, let's think about the chemistry. The dramatic colour change we see is due to iodine reacting with starch. Hydrogen peroxide oxidises the iodide ions to form iodine. However, we don't see this straight away. This is because a second reaction is also occurring. As soon as iodine is formed, it reacts with thiosulfate ions to form tetrathionate ions in a second, faster reaction. Effectively, the iodide ions are recycled. Once all the thiosulfate is used up, free iodine remains in solution and can react with the starch, thus forming our blue-black complex. So now I need to borrow some hands to help me get this started.
Okay, 3, 2, 1, pour.
Don't forget to start your stopwatch as soon as you add your solution to your conical flask.
3, 2, 1, pour.
Don't forget to record all of your results in a table. As my reactions are now finished, I need to dispose of the reaction mixture. The reaction mixture contains iodine, which can be harmful to aquatic life. As such, I cannot pour it directly down the sink. I need to dispose of it in the correct method, which in this case is to pour it into a beaker containing sodium carbonate solution. The sodium carbonate solution reduces the iodine to iodide ions. This can now be safely disposed of by a technician.